and several fundamental problems in mechanics, differential geometry, and the related area, and discuss some recent developments in solve these mixed type problems through this, the connections. So let me start with some background. Or as well known, three of the basic type of partial differential equations are elliptic equations, hyperbolic equations, parabolic equations. Follow the classification for second order PDE first proposed by Jacques Hadamard in early last century. So the representative of elliptic equations, of course, the Laplace equation, or sometimes we call equilibrium equation, with this form, which often describes the equilibrium state, the physical equilibrium state. Whose solution are called harmonic functions, sometimes we call potential functions. Then the representative of the hyperbolic equations is the wave equation, or Maxwell equations, which take this form, which describing the propagation of wave propagations. And of course, while the representative parabolic equation is a heat equation with this form. So these are three different type of equations, but they are connected, not really separated. For example, the solution of elliptic equations are steady state solution of wave equation and heat equation. On the other hand, the behavior of solutions, they are very different between the elliptic parabolic equation and the hyperbolic equation. One of them about the propagation speed, right? Infinite versus finite. The another behavior is the regularity. Okay, you get the gain or loss of regularity. Well, since the solutions of elliptic equation and parabolic equations share many common features, so in this talk I will focus on mainly about the hyperbolic type and the elliptic type and the mixed elliptic hyperbolic type. Okay. So distinguish between elliptic type and hyperbolic type can see very clearly from the second order two-dimensional constant coefficient, the second order PDE. So this is the second order PDE, the Aij, they are constant. Okay. Then this matrix we can consider the coefficient matrices, which is symmetric matrices. Then there are two eigenvalues. So we call this equation elliptic, means this matrix is positive definite. That means two eigenvalues, the same sign. This corresponding, that is a discriminant. Okay, the less than 0, bigger than 0. Okay, so this classification is just as we classify the conic sections on quadratic forms of quadratic equations in algebra geometry. One side, of course, you think about this conic section, you're cutting these cones, then you got the quadratic curves, the three different type of quadratic curves, parabolas, ellipses, and hyperbolas. This kind of classification also you can see clearly through Fourier transformation. You take a Fourier transformation both sides, then you got the coefficient with Fourier modes, cosine eta, then Fourier transformation of u. Then you will find the coefficient, this exact quadratic form. Now, if the equation is elliptic, then you can, this quadratic form have positive definite. You divide the quadratic form to right-hand side. So Fourier transformation of solution, you gain two order as the Fourier modes goes infinity, high frequency. Okay, so you gain two order regularities. While hyperbolic equation have degeneracy, right, along the wave cone, then you lost some regularity in some direction. Okay, so this is a difference for that. On the other hand, now if the coefficient set one of them, then you can make a quadratic transformation. You can second order PDE, actually you can transform that first case. If discriminant less than zero, you can transform to the two-dimensional Laplace equation. Same the hyperbolic is, you can make a just simple quadratic transformation. You can move to wave equation. Okay. However, for now, if the coefficient variable coefficient case, situation is more complicated. In this case, AI, J, of course, are not a constant anymore, depend in two independent variables, X, Y. Then again, we can do the same thing, compute the two eigenvalues. Then the type of equation is determined by the signature of eigenvalues. Really, for them, the two eigenvalues, you could change in some domain, the positive, some domain negative, right? So generically could be mixed type. So here they are listed now 3 fundamental equations of mixed type with this form. The first equation you can see sine coefficient sine function. Then if x bigger than 0, this is the Laplace equation. X less than 0, the wave equation. Now the second, third, the Jacobi equation, Keldysh equation, the coefficient, they are very nice, continuous, but they exhibit a different type of the degeneracy, okay, at x equals 0. Those kind of equations are related to many classical equations, famous classical equations like Poisson-Tapo equation, Bell-Chalmers equation, and so forth. Now for linear PDE of mixed type, even though they're mixed type, but we know the type of equation a priori in, we know the transition boundary of the like elliptic domain from the hyperbolic domain. Reason because we know the coefficient, the x, y exactly. So that means we know the boundary of the transition boundary a priori, right? So when we try to study this linear PDE of mixed type, you first start when we know where is elliptic with hyperbolic, which domain is elliptic, which domain hyperbolic. Then you first study like hyperbolic domain. Of course, degenerate near the transition boundary. Trying to understand degenerate PDE in the elliptic side. Then from hyperbolic side, degenerate hyperbolic PDE from hyperbolic side. Then you understand the singularity near the transition boundary. Then you hopefully get together, you get a global picture about the singularity of solution. Another approach is a global approach called fundamental solution approach. You first try to get the global fundamental solution, understand the behavior of the fundamental solution, especially near transition boundary. And then somehow you understand the behavior of solution near the general solution near the transition boundary. Now, today I would like to present a further perspective to show through several examples to show you that many nonlinear partial differential equations arising in the several fundamental problems which are still open, many of them, are actually not single type, but very often mixed type. So solution of those fundamental problems greatly require the deeper understanding of nonlinear PDE of mixed type. Now for nonlinear PDE of mixed type, then coefficient Aij is not only depend x, y, also depend the solution itself, or sometimes depend the gradient of solutions. So before you solve the problem, you really don't know transition boundary. Transition boundary really like free boundary problem. Free boundary. Before you solve the problem, you don't know which region is elliptic, which region hyperbolic. So until you solve the problem, you get a priori estimate or certain gradient estimate. Then you can decide, well, then can understand which part of the domain is this equation elliptic, which part of the domain is hyperbolic. Before that, you don't know that. So this is really one of essential difficulty. So many classical, very powerful techniques approaches for linear PDE of mixed type are no longer applied directly to that. So first example I want to present to you is from a shockwave problem from fluid dynamics. That is mainly the problem of steady supersonic flow or to solid wedge. Okay, so this supersonic flow, this is two-dimensional wedge, then coming from this far field. Then when supersonic reach to the this wedge corner, then it turns out you can prove that there are two solutions contain two different kinds of oblique plane shock wave. One called shock wave called strong shock, the other one called weak shock. Okay, there are two solutions. Both solutions satisfy equation in the sense of distribution and satisfy all physical principle entropy condition consistent with second law of thermodynamics. Okay. So one case there's a wedge angle if less than detachment. There are two solutions. For strong solution, the supersonic flow, then downstream flow, the state is the supersonic. Now for the weak shock, depend the wedge angle, sonic angle. If wedge angle is the bigger than sonic angle, then weak shock is still transonic shock. If wedge angle less than transonic angle, then the weak shock will be hyperbolic shock. Both sides will be supersonic. Okay. So this somehow involves a non-uniqueness issue here, right? The same problem, very simple problem, fluid coming in. It turns out mathematically you find two solutions. The question now, whether both solutions are physically admissible. If yes, how could we understand the non-uniqueness issue? Then, if not, then how could we one of solution be excluded from the other? So this caught the attention actually first by Planto. And here actually first one is the shock polar construct. That's two solutions mathematically. And from most of the physical experimental results, then you can see observe from them, then you find you are always observe weak shock solutions. The one solution which is red, I showed up here. So he at the conjecture the weak shock should be physically admissible. Okay. Then he also proposed the dynamic configurations. Now we call Planto-Mayer shock configuration, which when T goes, if this configuration exists, T goes to infinity, then asymptotic goes to the steady state solution, which is a weak shock configuration. So this is caught the attention of by the Coulomb Friedrich when they looked book this supersonic flow and shock waves. Actually, they spent quite a long two sections to discuss this oblique shock solutions. And then also they document the many the analytical result and experimental result before 1948. Now, through their explanation, they point out that here's the conclusion I put here. The question arising which of actually occurs, it has frequently been stated that the strong one is unstable, that therefore only the weak one could occur. A convinced proof of this instability has apparently never been given. So they believe that they somehow believe the Planto the conjecture, and then no proof has been done that. Then 1 year later, this von Neumayer quite got interested in this problem. He organized the panel discussion during this international symposium, jointly organized by the International Union of the Theoretical and Applied Mechanics and the International Astronomic Union. So he invited several the leading experts in around the world that day. Okay, like Burgers, Hessenberg, Lippmann, von Kamen, and others. And the topic is really discussed about the existing uniqueness of multiplicity of solutions of the aerodynamic equations. Then he started opening this discussion, and he basically talked about the same fact I just showed you. There are non-uniqueness issues. There are two solutions and different solutions. Now he pointed out it's perfectly well known from experimentation that only one of the two weak shock occur in nature. But I think that all stability arguments to prove that it must be so are of very dubious quality. So he was not very optimistic whether we could classify those problems, understand the problem through purely mathematical analysis. On the other hand, he pointed out from all experimental results, they show that always they observe the weak shock. The question whether mathematically we can prove that. Okay. Actually, I got into this problem 20 years ago when we started thinking about this problem. We thought, well, since 1950 to 2005, more than 50 years, there would be should be somehow many results, analytic results related to this question. Well, to our surprising issues, there had no significant really rigorous mathematical analysis, analytic result to address understand the problem, especially the stability argument, as von Neumann point out. So we started now the problem trying to see whether those steady state, the solution regarded as a steady state, then can we show whether the solution stable or unstable under perturbation is a steady framework. You perturb income from a steady flow and perturb the wage. Can we get understand the stability issues? It turns out now through the 20 years, this has been quite now relatively well understood now, physical admissibility in terms of steady case. Actually, for weak supersonic shocks, the first result was a week I could find Gui-Qiang from Fudan University about local structure stability. Then Schaffer, Li Dajie, Su Xinzhen, they discuss the stability of the weak transortional locally. This is all stable. Then you can, this it turns out they can prove now even much weaker perturbation like BV perturbations, still stable globally even. Now for transonic shock, situation more subtle, but this has been done now for weak transonic shock and strong transonic shock. So this is done. This now recently also will understood now for even multi-D stability, not the two-dimension, which is a high-dimension case. Just list some of papers. There are more papers actually. In the I could not put all names here. I just listed some of them have been done. So what we understood is for steady this perturbation for stability of statistical stabilities is the following. So weak shock as a supersonic or transonic shock, they're always stable, very general class of perturbation, they're always stable. Why we understood the experimental could not see the strong shocks? The reason because strong shocks, you're not always stable, but stable depends on your class. You have to select this perturbation class very carefully. Then mathematically, you still can prove stable in that class. Generically, it's not true somehow. So maybe very difficult to see from the experimental for strong shock, observed strong shocks from this analysis. The question, of course, more interesting, of course, what about dynamics, right? What's going on? So this is related with the Planck-Mayer configurations. Actually, Planck-Mayer configuration shock comes there are two cases. One case is the depends sonic angle. If sonic the wedge angle less than sonic angle, so behind the shock, is here, start here. Behind this point, this will be supersonic. Then if wedge angle less than sonic, then the shock at this point attached shock at the corner will be supersonic. So this is related with like a supersonic plane-to shock configuration and supersonic plane-to mirror shock configuration. The question whether this weak shock is physically admissible dynamically from you can try the solution that G goes infinity to select the weak shock solution. So now then you may say, well, this problem is so concrete, the shock wave problem. Why you are so many people interested in this problem? Well, there's one much deeper underlying reason is that if we think about the two-dimensional hyperbolic conservation law, is first try to understand the two-dimensional Riemann problems, and then actually you can find Riemann problem means the two-dimension is the XY plane. The initial data only depend the angle. Okay, so this class of initial data called Riemann data. Then it's easy. You can choose design some Riemann initial data. Then you find some configuration of Riemann solution is the form as I show you here. It's called plane-to-mirror configuration. On the other hand, the Riemann solution is really fundamental. Theoretically, play the determine asymptotic state and attractors. Also, the determine local structure and building block of general entropy solution. So it's essential if we understand the general entropy solutions, we should understand the Riemann problem, Riemann solution first. But one of the configurations is really related with the plane-to-mirror configuration. Okay, so let me start explaining this problem. Let's first focus on the Euler equation for potential flow. Potential flow case, the velocity you can represent by velocity potential phi. Then equation, first equation conservation mass, okay, lower the density. Then second equation Bernoulli law. So this equation consists two equations. One more or less like first equation, more or less if you know the phi velocity potential, this will like transport the equation basically. The second equation, really, if you know density, this is the Hamilton-Jacobi equation. So all equation potential are very beautiful. The coupling between transport equation and the Hamilton-Jacobi equation. Now, if you from this gamma is constant, any constant, adiabatic constant in gas dynamics. Now, if you represent the density in terms of Gaussian phi, prime first equation, then this is called the nonlinear wave equation. Okay, second order nonlinear wave equation. So this is actually one of the early motivation why we're interested in the nonlinear wave equation, second order PDE for that. Okay. So this is a PDE. Now focus on that. Then the question: can we find a solution with this plane-to-mirror configuration as the solution of this PDE, the Euler equation for potential flow? So whole problem really is the initial boundary value problem, right? Physically set up. Initially, t equals 0, I give incoming flow, this supersonic flow. Then I want to find a solution with a satisfied slip boundary condition of the wedge boundary. Right? So this becomes initial boundary value problem. I have nonlinear PDE, PDEs, then the initial condition and the slip boundary condition. The configuration I show you suppose the solution of this initial boundary value problems. Okay. Now, if you look at this problem carefully, you find that this problem actually turns out invariant and self-similar scaling. If you're scaling Tx with this form for any alpha, I saw alpha not 0, low phi in this form, then equations, those equations are invariant. Initial conditions invariant, slip boundary condition invariant. So it's nature you're looking for solution called self-similar solutions. Now for self-similar solutions, you introduce original x1, x2, then cosine eta, then density. Now original 3 variable become 2 variable, independent 2 variables. Now, for convenient, we velocity potential are shifted by quadratic terms here. Reason I shift that, I can rewrite now equation very beautifully, which is the quasi-linear second order nonlinear PDE. Okay, independent of independent variable cosine for this phi. Okay, so just shift the phi. This for convenient. Then this makes this second order PDE very nicely. It turns out the second order PDE is not purely elliptic. Okay, it actually mixed elliptic and hyperbolic. This is the first example I want to show you. Very naturally from very classical physical problem, it turns out they come out as a nonlinear PDE with mixed elliptic and hyperbolic. Now, when this equation elliptic, when grading phi less than this relation, function phi, otherwise that. So this is really second order nonlinear PDE of mixed elliptic hyperbolic type. So before you solve the problem, after you don't know in which you consider in which region the solution is elliptic, which is hyperbolic. Unless you solve the problem, you get a grading estimate. Then you will say, oh, this is the elliptic equation elliptic, then some part domain the equation hyperbolic. Those kind of equation, of course, there are more early equations, model equations are just called GSDE equations with these forms. And there are other nonlinear wave equations, then pressure gradient equations, then the steady potential flow equations, like all mixed type. It's a little simpler than I showed you earlier, those mixed type equations for that. So original then, instead of similar coordinate, original initial boundary value problem become boundary value problem in unbounded domain. In self-similar coordinates, still keep the same slip boundary conditions, then asymptotic initial condition become asymptotic condition. Okay, you want to match my solution when cosine eta goes to infinity, match this incoming flow state, physical state. Okay. So the whole problem now reduced to initial boundary value, now reduced boundary value problem in unbounded domain for mixed elliptic and hyperbolic type. Okay. It turns out we can further reduce the problem. And it turns out you outside the hyperbolic, from infinity coming here, actually you can solve the basically hyperbolic part of the nonlinear wave equation. You solve hyperbolic part, actually you can find out, you can determine actually two shocks here away from the wedge vertex. You have a normal reflection shock, uniquely, location can be uniquely determined. You can determine state behind the shock. Also on the corner, we choose now weak shock. Then you can, by shock polar, you can determine income flow, you can determine state here. You can determine the shock slope as well. So this part we can solve the purely through hyperbolic theorem. A solution are unique. You can do this way, this part. This one you choose the weak shock. The whole part really, now this is hyperbolic, although this region hyperbolic. Then hyperbolic will degenerate up to certain circle, they call sonic circle. This sonic can be determined, this sonic circle can be determined. The whole problem now, how to solve find a solution in this part of the region, outside the hyperbolic, whether we could solve the shock, then inside will be elliptic. This shock you can form a free boundary, basically. So there's a mixed type of problem. One phase hyperbolic, other phase elliptic. Then this elliptic will degenerate on this between the two curves. If we can find a solution, then we construct the Planck-Mayer configuration successfully. Okay. Now here I mentioned the shock several times. At least I see something about shock waves. Shock waves really are discontinuity, two-dimensional one discontinuity wave. In this case, the pseudo velocity with respect to pseudo velocity including phi. You have like one side, suppose we have shock separated by two regions. Both sides satisfy equation, satisfy potential flow equations. Then we call this two-dimension wave curve is shock means satisfy two conditions. This is called Rankin-Hooker conditions. Phi should be continuous, but normal derivative should jump through that. So this condition, you want to make sure you have two solutions, two regions, then put together through discontinuity. The question whether put together still solution of partial differential equation in the sense of distribution. It turns out not always true. Necessary sufficient condition is these two jumper conditions. So physicists of course this jumper called Rankin-Hooker condition, but mathematically we just want to put the two separate solutions we put together, want to become global weak solution of the nonlinear PDE. Then this is a necessary sufficient condition. So this short weak solution, this kind of jump not unique. Then you require entropy conditions. Through the shock, in this case, the density function increase close shock in pursuit of velocity direction. This really consistent with second law thermodynamics. Okay, you want to apply that. So this kind of two-dimension one surface we call shock waves in high dimension. Okay, so this is what I point out. Shock based on these two conditions we calculated, then you can determine the location of shock in this form. Okay. So another thing about the constant state. The constant now, physical constant. Now, if you remember, I introduced potential function shift the quadratic form. So for constant, for this solution phi, actually quadratic forms. Okay. So this form now, although this solution for this is a very constant density case, but this actually is a solution of PDE with contain mixed type. There's a sonic circle. For this equation function, plugging PDE in the region called inside sonic circle, elliptic, outside the hyperbolic. So for constant case, this is still this reason why the constant determines the sonic circle, determined by this sonic speed, basically. So this is what the degenerate hyperbolic occurred, and from straight hyperbolic become degenerate hyperbolic from inside. Outside will be elliptic. So even this is very trivial physical solution, but still, in some sense, you still solve the PDE of not mixed elliptic hyperbolic. So this is the reason we that type of solution in this form eventually. The question how to solve this problem. It turns out really becomes from the free boundary value problems. Now I just show you angle less than sonic angle, and then you're looking for, basically you're looking for this free boundary, this is called transortial. With now this fixed boundary, then inside we want to find the solution inside this elliptic solution, supersonic. So this is a part of solution result. Before you solve the problem, you don't know inside the elliptic or hyperbolic. Okay. So we want to construct solution inside the elliptic. Then the free boundary satisfies two conditions. Then again, there are two degenerate curve sonic circle, and actually, because the same reason like a Rankin-Hooker condition, after we solve the problem, you put together one global solution. It turns out they require two conditions on the sonic circles. Okay, degenerate elliptic curves. So generically, you cannot give two conditions on for elliptic problem. Now, since this is boundary degenerate elliptic, then there's hope we could match two conditions. Now, if it's uniform elliptic, of course, deletion data, you cannot add one more condition. So this has to be very careful to analyze degenerate elliptic equation, see whether the two conditions match, then in order to get a global solution. So this kind of free boundary problem have been studied in the large literatures. Basically, two framework. One is the variational formulation. If you can formulate the variational problem, then you take a minimizer, then you get to solve the free boundary problem. Another approach is the Pelot method for linear PDE, through the Cavalieri approach to find the free boundary solution. It turns out this problem actually could not formulate the variational problem. Then also this free boundary cannot, it's nonlinear. So we have to really require develop new techniques to solve this free boundary with new features. Then whole problem really want to find the two solution for. First is the supersonic configuration, a wedge angle less than sonic angle. Then want to beyond the sonic angle. Then the question another optimal regularities. Now for the first case, supersonic configuration, they are result by Allen Liu 2008-98. Then they have condition when certain parameter regime, basically they want to now the sonic take a straight line. You want to prove if the parameter satisfies that sonic circle start at U infinity 0 is not touched to that line, then they could do it. Okay, so this is related with like a wedge angles small or certain gamma, certain increment block, then they could construct solution. So now later on, we now think about whether we can do all parameters, also even beyond the sonic angle, or what we could do for that. So this really, like I explained earlier, this involves several mathematical challenges. This involves nonlinear PDE, mixed elliptic-hyperbolic type. Also, we require new approach for free bounded problems. Then another thing, really we require optimal estimate for nonlinear degenerate PDEs, especially along the two sonic curves. Then the corner, okay, corner singularity near the like a free boundary meet this degenerate curve, this corner. Another thing, the beyond sonic circle is now shock with the wedge angle. How to do that? It turns out the mini elliptic theorem requires the Gauss conditions to study this oblique boundary condition on the corner. And it turns out our problems without the Gauss conditions for the corner singularity. So somehow we have to redo this kind of theorem about corner singularity without the Gauss condition before solve the problem for that. Then another, of course, we want to see geometric property of Chen shocks. But turns out we can prove now this is the result we actually now that will appear in the memoir AMS, hopefully this year or early next year. The answer is yes, we can do it now. You can solve this free bounded problem, and the inside the really elliptic, outside hyperbolic, and the solutions inside of course infinitive, the free boundary C infinitive, even analytic, then actually C2 connect to the other shocks, not only slope, also curvature. Then we also get through the transonic shock, we can prove C11, okay, through that. And C11 is really optimal regularity somehow near the corner. Then we got the various property for that and as well. Then also we can do now the beyond the sonic angle and the supersonic case. You get a solution, this form, and you got the optimal regularity as well. Okay, so somehow we answer the question for this problem through this careful analysis for that. So approach of this related technique, without the previous preparation, we could not solve this problem. The approach and the related technique has been developed based on the ideal technique from our early work when I worked with Mr. Feldman about the shock reflection deflection problems. Based on that, now we use those based on those ideas. Now we can solve this problem somehow. Okay, so main part I just quickly mentioned the iteration. Really, to solve this problem, you use really Rayleigh short degree theorem to do that. To do that, Rayleigh is first 1, 2, 3, 4. 4 points is essential. You get the a priori estimate, okay, for various estimates about monotonicity properties, the C01 estimate, uniform estimate, and the C2 alpha estimate, so forth. So this estimate really takes almost 100 pages. After this estimate, then we set up the iteration set interrelation map, then we can prove this, fit the whole problem fit into this fixed point framework with low Rayleigh short degree theorem. Then we can do it. Okay. Now, what about the strong case? You know, strong. This is a normal shock. Then I pick now with strong shock. Can we construct a supersonic solution inside? Okay. It turns out now we can be sure the no existence actually. Difference between weak shock, strong shock, this normal boundary condition is the direction. Okay. For weak shock, you have one freedom. You can choose one data, additional data, then make the shock continuous. The other one, you cannot get additional conditions. Then it turns out impossible to get the weak shock. So this way we prove the weak configuration. It's really globally as asymptotical to weak shock, but strong when you cannot get this kind of configuration for that. So recently, actually, we based on this analysis, we can now even prove the geometric properties about all those kind of transform shocks, which are basically you can prove uniform convex, except of the ending points. With that understanding, now we can get because uniqueness, stability of this global shock reflective and configuration with respect to Gui-Qiang. I should point out those kind of geometric property are studied for free boundary problem for various problems. I list some of them and include in some water waves as well about the convexity and others. This is for potential flow. Now, if you think about 4 Euler equations, then you self-similar, then you actually have 4 equations. Then this 4 equations, you can find the 4 eigenvalues. Then you compute, you will find actually 2 equation transport equations, and the 2 equations are mixed hyperbolic elliptic type, as I showed you earlier. Also, you can use Cauchy decomposition. This 4x4 system, you really can decompose one part is potential flow equation coupling with the 2-dimensional incompressible Euler equation actually put together. So this is the kind of mixed nonlinear PDE appear many places. Okay. So this is several examples, basically 2 examples. I show you the mixed elliptic hyperbolic occurring fluid mechanics. Now next, I will 10 minutes, 15 minutes, I will show you another example from differential geometry. Is about the isometric embedding problems. Okay. So this problem set up very simple. We know that you give a curves, okay, then surface, okay, then you compute the second fundamental form, and you have second fundamental, first fundamental form, and second fundamental form. So problems opposite now. We ask, we're giving metric or giving certain property of curvature. Can we construct the surface in R3 in Euclid space or generalization, high dimension Euclid space? So this is like an inverse problem, right? You give the metric or some property of curvature. Can you find the surface you want, right? It turns out that this statement is very simple. It turns out this problem is very difficult. Still, whole problem in generic case still open. Okay, this problem very important, right? In the different geometry topology and in many applications, and many mathematicians, especially geometry, differential geometry and the geometry analysts, they're working on this problem start the last century. Like Dabo, here the Shirley and Dabo Hilbert, and up to now, the various results now obtained. As I point out, the many problems, generic case, most cases still open. Reason because I want to show you this involve mixed elliptic and hyperbolic, PDE of mixed elliptic hyperbolic. Okay. So for this problem, Nash actually proved the following theorem. If you target the space, the Euclid space Rn. If n large enough, then this is in this form here is in Janet dimension, optimal dimension. Now, if n large enough for compact case or non-compact case, if n large enough like that, then you can prove it. You find that isometric embedding surface. Okay. The problem, of course, especially important for application, you really want to get optimal dimension. The first point. The second, of course, the rigidity. Okay, the isometric band, where the rigid. Nash is, yeah, the one case rigid, the other case, yeah, it's when I will explain later on the issue for that. The second of optimal regularity. You know, what kind of optimal or assigned regularity? But this regularity also very sensitive in this problem. For example, if mostly give a kind example, actually for n equal to s equals 3, there are no C2 isometric banding. So this is interesting to think about. The regularity also becomes very sensitive. Now the water connection with the PDE, okay, the mixed type equation. So they come to the fundamental theorem of differential geometry. Theorem said if the surface is 3 dimension, there exists, you can construct surface. If you give first fundamental form, and if a second fundamental form satisfy Gauss-Codazzi equation, okay, compatibility conditions. This is the Codazzi equation, is the Gauss equation. Then the 2-dimensional manifold, you can get R3 construct surface. Okay. So this is a classical theorem of the start analytic C infinity CK. Actually, this theorem also holds if second fundamental form in LP. Right? This is Nadali proves that. So now, what is the Gauss-Codazzi equation? Gauss-Codazzi equation for second fundamental, I'm scaling that. So ML satisfies first order PDE. Now, then constrain with the Gauss equations. Okay. So the 3 unknown, then you have 3 equations. Then turns out this PDE actually, if you, of course, you know LM, you replace L into the first PDE here, then you got the first order PDE. And then turns out this PDE is a mixed type elliptic hyperbolic, depend the Gauss curvature, basically. If Gauss will be positive, this way elliptic, otherwise hyperbolic. So the find a solution, this mixed elliptic hyperbolic is one of the key points to construct the isometric embedding surface. Well, this Gauss curve change time very nature, you know, like Barnard's, Taurus, this is change Gauss curvature. So PD point with the mixed type elliptic are very generic from geometric point of view. And then recently we, the few years ago, we thought, well, this piece kind of features similar like fluid dynamics. So why can we see something about fluid dynamics? Can find fluid dynamic formulations for formalism for isometric embedding. It turns out that for this case, we could do it now by introducing LMN with this form. Then you got the balance law of the momentum equation. The Codazzi equation can write down represented by balance of momentum equation. And the Gauss equation really become Bernoulli law relation. Okay, so the first example I give you potential flow is the conservation mass and the Bernoulli law. It turns out the Gauss-Codazzi equation come out the momentum equation coupling with the Bernoulli law somehow in this format. Then we also found, well, this is very nice to match this flow, the Gauss curve bigger than 0 really match to supersonic region. The flow Gauss curvature less than 0 supersonic. So this is like related to supersonic mixed type transonic flow problem basically. Okay, so this is it's really a nice connection between the geometry and the fluid dynamics. Based on this understanding, then we found a way to prove the wave continuity and existence of this Gauss-Codazzi equation through the wave convergence method. And listen to there are quite many activity in this under this line. Now this is two-dimension, two manifold, three-dimension manifold R3. What are the high dimension? High dimension, then PDE will be Gauss-Codazzi-Ricci equations and systems. And then this is really in genetics a very big system. Okay, and this PDE is Gauss-Codazzi-Ricci in genetic no type. Okay, it's proved actually it's impossible to become elliptic all the time genetically, and but mixed type elliptic-hyperbolic, then genetic is no type. Okay, as a purely hyperbolic or non-purely elliptic for general Riemann curvature tensor. Okay, unless you have restriction about Riemann curvature tensor, otherwise genetically no type. There's a little work, many works talk about the type of PDE and so forth. In any case, 10 years ago, and I joined with Marshall and Slammer and the one we found, actually this system, like Gauss-Codazzi-Ricci, has beautiful structure. Observed the at the core structure, and we can prove that we can limit the field of sequence of solution, limit to still solution of Gauss-Codazzi equation, as long as they bounded in LP. Okay, so main idea behind that is that the structure, we observe that difficult structure of this system. As you can rely the Gauss-Codazzi and the Ricci equation in the difficult forms, actually. Now you really want to pass the limit through this nonlinear term, this quadratic term here, quadratic term here, quadratic term here. They have to pass the limit through the quadratic term, the wave continuity. It turns out we construct a observe this difficult structure, then use difficult lemma. It turns out exactly produce this quadratic form weakly continuous. You can get the all pass limit exactly. So this is really beautiful structure and like God given. Somehow the bounding is like LP boundaries give you this difficult relation, the compact H-1. On the other hand, H- and compactness give you weak continuity of quadratic form pass limit. So this is the slope that eventually can get it. Yeah, pass limit. So this is really independent of type. Just so we don't care type. Really structures plays a role. This is just an example I give you. And this related with the difficult lemma. And the classical differential start Muller, Tata. They talk about the solution. You have sequence, one sequence weakly LP, another sequence LQ. Of course, this implies difficult is bounded in W-1, W-2. If you ask a little more, this difficult is compact in this space. Then this inner product of the two vectors, of course, LP is this vector series L1, right? Uniform bounded. Now L1, genetic weak convergence is not in L1 anymore. Could be measured. But now if you know a little bit about compactness, then limit not only L1 still, but weakly still it can represent by inner product. So this is very beautiful lemma in the classical way. This lemma now has various extensions for various different applications. I just listed some of them here. And we listened a few years ago with Celine, we extend this kind of lemma to now a theorem on Banach space. Basic key point is like this operator. It's two operators orthogonal. This is a key point. Because difficult there's this property, differential operator. So you can set up in the Banach space. You can put this form, then later put this condition for this adjoint operator. Then sequence, you're given two sequence. This operator act on this sequence as this property. Then you still keep the weak continuity over the Banach space. Okay. So this Banach space is a very general setup. It turns out we're very useful to got this weak continuity of Riemann manifold intrinsically independent of coordinates. Okay. This has been also further generalized recently with my student Gui-Qiang, even more general setup. It turns out this now we can use that with continuity of Gauss-Codazzi equation for general surface Riemann manifold independent of local coordinates globally. You still can prove the theorem with convergence result. Okay, then this imply, of course, weak rigidity of isometric merging with given curvature, the second fundamental forms. So this kind of compensate theorem on Banach space really help us to do that. This actually we can now. This of course we assume both second fundamental for normal bottom connection is bounded. Now we can remove now this thing the normal bottom, normal connection. It basically just only need the second fundamental form for high dimension case, and then you can get the result the refined sequence. Based on that sequence, you can find the refined sequence, the limit to still satisfy equation of Gauss-Codazzi equation. Okay, so this is globally independent local coordinate and no restriction of Gauss limit curvature of type PD. Here we have to use now some invariance of choice of for gauge to control for the connection form. So I hope, yeah, this is the example I just give you that about weak rigidity earlier. Now we can do more somehow. In summary, I will say global weak continuity and the Gauss-Codazzi-Ricci equation are manifold with local regularity. We can now I explained now earlier about Riemann manifold. You can also do semi-Riemann manifold and give a uniform intrinsic approach for weak continuity. And this is related with, of course, result of the weak rigidity of the isometric embedding. Then the problem I just discussed really motivated by early work, many early work in elasticity. For them, theorem of polyconvexity by John Ball and many others, and some others. Then also intrinsic method, intrinsic elasticity, nonlinear Kahn inequality by Professor Ali, and also the connection with the listening to activity now about convex integration flexibility by Gromov, Delele, and Sikahidi, and many others. This idea now we listen to, we also apply to Yang-Mills equations and works very nicely. And this motivated early work like Uhlenbeck, Donaldson, and now also recently Liatichi Temple. Few years ago, actually, I just give you several examples now. Few years ago, I joined with Griffith and Robin. We edited a book called Differential Geometry and Continuum Mechanics. We collect other examples which involve nonlinear PD of mixed elliptic-hyperbolic type. If you are interested, maybe you could check that. So I hope I convinced you. Already have convinced you that the nonlinear partial differential equation of mixed type, or even no type, naturally arising the many fundamental problems in fluid mechanics, differential geometry, elastic, and other areas. The solution to those fundamental problems in area greatly requires deep understanding of nonlinear PD of mixed type, especially elliptic-hyperbolic type, and require further development of nonlinear mathematics. So I stop here. Thank you very much for your attention.
Okay, so let's thank Professor Chen for the really wonderful talk. Any questions and comments? Any question or comments?
Yeah, Professor Chen, can I ask one question?
Oh yeah, Shabin.
Yeah. Okay, so in your section, you are basically you are considering the forward self-similar solution, right?
Yes, yeah.
Yeah. How about the backward self-similar solution for the Euler equation?
Which one, backward?
Well, yeah, backward. Suppose initially the solution are smooth, and in some time capital T, there's some shock. So can you do similar work for the backward?
Oh yeah, I see. You mean some t minus t, capital T minus T.
Yeah.
Oh yeah. You could do the that should do the similarly. Yeah, if leaving the problem, the T is really, you could scaling T, no problem, right? The setup problem.
Yeah.
Original. So you can put the T minus T, then of course you get the sign 1 minus, So this is still, still the mixed elliptic hyperbolic.
So the result could be very similar, right?
Could be, Go differently, now there's the entropy condition issue, of course. Now, if you reverse the time, because the whole process is irreversible, right?
Yeah.
So then you have to do other way along somehow.
So maybe we will get you will get the trivial solution in some sense.
That's a good question. Yeah, interesting if you do this way, because this whole part is the time irreversible. If you do reverse, then you have to different structure will be different. Problem still, mixed elliptic hyperbolic. You have to change the entropy condition. This is a very good point. Then with different way, of course, different physics, right? This is very good. Mathematics.
Maybe another question. Okay, so in your two-dimensional case, you used rotational assumption, right? So U is correlational fact. So I think in some sense, in three dimension, you can also assume the rotational assumption.
Yes.
So
you're right. This you can. You're right. This is good. This is the same. You can set up the same thing now. For example, you do wedge by cone, right? The shock coming the cone there. And then the question that still involves shock reflection, deflection problems. The actually, we are working on that. Now the more problem, the more complicated. Several issues. One, of course, like state 2, we hear the constant state. Then the 3-dimension have to solve self-similar solution, not the constant hyperbolic region, not a constant state anymore. So we first have to solve hyperbolic part. Then the sonic circle will be not a circle, will be degenerate curve. The hyperbolic city field is the degenerate set. Another difficulty, we have to rely the elliptic theorem if supersonic case. The 2-dimension, you see, we don't have Gauss conditions. Then with 2-dimension, we found a way to do it. 3-dimension, we have to think about the conic, the corner, the cone with shock, the corner, right? About regularity, optimal regularity, the corner. And without the Gauss condition, we had to set up to solve this corner problem, 3D high dimension problem. It's not actually interesting. They're not available yet. We have to do that as well. Then it depends spectrum, 3D spectrum, even linearized problem, spectrum more complicated than the 2-dimension case. So there are, this is excellent questions. Still, there are a lot of open questions in this direction. Especially the next level, 2-dimension to 3-dimension or high dimension. Require new mathematics, really new techniques, even. So we somehow just start.
Okay. So as for the 3-dimensional case, it's basically reasonable to consider the solution with some kind of symmetry, for example.
So chronic case, the many experimental result. If the cone, right? So here there are many experimental results like a similar structure.
Okay. So
the question how to prove those structure, construct a solution with this structure. So actually involves you develop elliptic theorem and hyperbolic theorem both. There are many new questions, new issues there behind that. before they solve the problem. So it's a very good motivation that the problem, those people work interesting degenerate elliptic, degenerate hyperbolic, and corner singularities. Yeah. Mm.
So also for the two-dimensional case, the regularity of solution is in the Holder space, not in the general subunit space. Can you approach in that direction?
You mean which is the Holder space? Oh
Yeah.
yes, yeah. There's some the actual potential flux we're doing the Holder space. Yeah, mostly. The supersonic. Yeah. That's another. Yeah, right. You could do subunit versus Holder spaces. The special talk of spectrum. Yeah, it's right. It's you can set up a problem at different spaces. Yeah, it's also very interesting.
Okay, thank you. Thank you.
Yeah. Thank you very much. Yeah. Oh yeah, that's a really excellent question.
So any other questions? So I ask maybe the last question. Yeah. So last one for the geometric problems. So because you talk about something without the type, you cannot classify the type of equation.
You're right. Yeah.
So in that case, if the embedding is, we require the embedding is smooth.
Yeah.
So even for the local, any results of that type?
You mean smooth embedding?
Right. This is what I mean. Even local.
Locally, yeah. Locally, yeah. With the result, I say, when I mentioned, of course, there's the early result. This locally, there's there one point on the transonic point. Then locally,
it's quite similar to that, I guess.
Yeah, this is the CC link. This two-dimension manifold to three-dimension. Actually, CC link did that. Then now the generalized. He degenerates one order. Gauss curvature 0, 1.
At 1 point.
Then the order high order. Now there's a paper about this locally. You can do that. Now high dimension, actually, we have the paper now. I mentioned that I didn't have time to mention here.
Yeah.
Actually, we published the Ancient Journal of Mathematics in Hong Kong.
I see.
This is a 4-dimension, 3-dimension manifold to for 6. Yeah, this is locally. Yeah. We prove the local isometric embedding, the Gauss-Codazzi. There's no type now in general. Okay, this case, the high dimension. Yeah. Then it turns out we found we observe this system also a very big system, but we found this system has a positive symmetric structure.
Oh, that's very nice. Yeah.
So this is purely idea, the Schmidt-Lich idea, the system, the symmetric. So we use this positive symmetric structure. Then we prove, the local asymmetric embedding.
Yeah. People didn't observe that. Yes, that's right.
Before they used actually we identify hyperbolic ellipses in some part. Brian, Griffiths, Young, they use trying to identify some state the system hyperbolic. They prove very complicated. Use geometry, algebra geometry. There's a variety calculation, various variety. Eventually, they like 100 pages. Identify some state of the system hyperbolic.
I see.
So we found identify system as a positive symmetric structure. Yeah, so much simpler from PDE approach side. Yeah. Then we prove the locally symmetric smooth symmetric embedding high dimension.
Yeah, very nice. Yeah, I see. Yeah.
Oh yeah. We were kind of happy with this paper actually.
Very nice. Yeah.
Use PDE approach, purely PDE approach.
So let's thank Professor Chen for a very wonderful and enlightening talk. And thank you, Professor Chen. And so we
thank you very much for your
here.
Thank you.
Okay. See you in the future. Not on that, but
looking forward to see all of you in person. Hopefully we'll finish the end soon. The pandemic will end soon.
Hopefully. Okay, so let's finish here today, and so everybody have a nice evening, and Professor Chen have a nice day. Yeah. Okay.
Oh, thank you very much. Yeah, thank you.
You're welcome. Yeah. Bye bye.
Bye. Yeah.
拜拜。
Yeah.
好，谢谢罗涛。
没有，谢谢。好的。
哦，谢谢罗涛呀，罗涛。
没有，我开始的时候进去，因为我是 host， 我也用他们那个 link 进去，我整了半天没整好，所以当时很急，到5点才搞好。好，不好意思。
Yeah, the internet connection is sometimes a problem, really.
对，因为那些 link 搞不清楚是用哪一个。
Right. Yeah. It's sometimes also not so stable, even Zoom better than others.
That's right.
Still not very stable. Yeah. So you are doing well, right? Your whole department doing well.
Oh yeah, okay. Not bad. Yeah.
It's,
So
we haven't seen each other for a long time.
For a long time because of this. This the COVID-19.
Right.
That brought people.
Yeah. Well, maybe hopefully vaccine will work.
Maybe next year will be okay. Yeah. Hopefully.
So far well, but still not reach to the level.
To
maybe
travel.
70%, 80%.
That's right.
Maybe reach to 90%. Then will be.
Then they should be okay, huh? Yeah. Okay, so you're in the afternoon or morning?
We are still morning now.
Oh, morning. So it's almost lunchtime for you.
Oh no, 10 o'clock actually. You
okay. I see.
You should go dinner now, right? Yeah.
Almost. Yeah. Okay. So it's very nice to see you here and then listen to your wonderful talk, and very nice.
Well, some of you already know. I thought this is more general audience, so so probably I'll repeat some of them. Otherwise, if the PD seminar, I will just focusing on some of,
For this, for a general audience, and so you give a very general picture for people, and people can see the big picture and they get the ideas and what's going on. Very nice and wonderful.
Well, hopefully, okay. Hopefully, you will not feel disappointing.
No, very nice. We are very happy and to learn a lot.
Thanks.
Okay.
Well, I'll let you go. You have to go like dinner anyway.
Thank you so much. And
okay.
Bye bye.
Bye. See you.
Bye.
Thank you.
Bye.
See you.
Bye bye.
You should go dinner, right? Yeah.
Almost time. Yes.
Oh yeah.
Yes.
Bye bye.
Okay.
Bye.
Bye.
Bye. Keep in touch.
Yeah.